Hello, everyone. My name is Zhou Huan Chen. I'm a postdoc from Columbia University. The topic I'm going to talk about today is representation and normalization of complex interventions for evidence computing. Intervention is one of the major components of the well-adopted framework, the PICO framework, which is used to formulate clinical queries to support evidence-based medicine so as to improve the decision makings about the care of individual patient. And the involvement of multiple components and internal arrangements result in the complex interventions. For example, the brodalumab 210 milligram every 2 weeks after receiving ustekinumab through 52 weeks. In regard to medical evidence computing, it is important to normalize the intervention into structured representations to support the structured query. And there are several existing systems for the normalization of interventions, such as MedXN, MedX, and HEMONC. Those systems either enable a limited range of interventions to normalize or not able to capture the internal relations or attributes of the intervention. So our study aims to better normalize the complex interventions, and it is developed into two aims. The first aim is to design a compositional model for the representation of complex interventions. And the second aim is to develop an information extraction pipeline, which takes in the free text complex interventions from randomized controlled trial abstracts and convert to a computable representation. Two independent datasets were created and used in our study for the development and testing of our representation. The development dataset includes 3,447 manually annotated intervention snippets from 261 RCT abstracts on PubMed, and the testing dataset contains 361 intervention snippets extracted from 29 unseen RCT abstracts. And here, the left figure shows the semantic network of the compositional representation. Each intervention contains one or more intervention components. An intervention component is an atomic treatment entity represented with its negation status and modifying attributes. And the subclasses for the treatment entity include device, activity, procedure, and drug. Each treatment entity is normalized to a URS concept. The attributes include duration, frequency, strength, route, dosage, form, volume, and count. Some of the attributes are specific to particular treatment entity types. And for the intervention, we also defined an attribute, component relation, that captures the internal relations between the intervention components. We identified 6 types of intervention relations, combined with, or, before, after, substituted for, contain, and without. The red column is corresponding examples. The first 2 relations, combined with and or, are non-directional relations, and the other 4 are directional relations. The before and after relations are integrated by reversing the directions between the intervention components. With the designed representation, the second aim is to develop an information extraction pipeline. The pipeline contains 4 steps. The first step is preprocess, and second step is treatment entity extraction and mapping. The third step is component relation extraction, and the last step is attribute extraction and association. And here again, we use the example brodalumab 210 milligram every 2 weeks after receiving ustekinumab through 52 weeks. At the second step, two drug entities were extracted and mapped to the UMS concept. And at the third step, the relation before-after is extracted. And at fourth step, the strength 210 milligram and frequency every 2 weeks were extracted and associated with brondalimab. The duration 52 weeks was extracted and associated with ustekinumab. Both drugs have the negation attribute affirmed, and the red figure shows the structured output. And here shows the detailed description of each step. The pre-process involves abbreviation resolution. For example, the SOC is expanded to standard of care, and also text cleaning. We remove special characters such as parentheses and hyphens. And for the second step, we used quick UMIS to identify and map the biomedical terms to the UMIS concept with 34 semantic types that belong to chemical and drugs, activities, procedures, and device. Then the boundaries of the terms are expanded based on the syntactic information. For the third step, we used a pattern-based method to extract the component relations, and we used a hybrid approach that combines dependency parsing and pattern matching to identify and associate the attributes. The patterns are extended from MedAxon. As for the evaluation, first, we remove the duplicates and irrelevant snippets from the 361 interventions and return 170 interventions. Those snippets were independently annotated by two annotators. The disagreed annotations were then discussed and re-annotated based on the annotator's consensus. We used the precision, recall, and F measures as the evaluation metrics. Here, the figure shows the overall intervention complexity of the evaluation intervention snippets. Of the 170 interventions, around 75% interventions contain only one entity, and the drug and procedure dominant in the types of treatment entities. For the component relations, we identified 43 interventions with the predefined relations, and combined with appeared the most times. And as for the attribute types, the frequency, duration, route, and strength appeared more than 10 times, whereas form and dosage have 6 and 7 counts respectively. The tables here shows the performance of the pipeline on intervention entity extraction. We evaluated both exact match and partial match on the extracted treatment terms. Drug, activity, and procedure have high F measures on exact and partial match, whereas the F measures of exact match on the device entity is relatively low. There are several possible reasons. First, some terms cannot be mapped to a proper device concept on UMLS, and sometimes it is difficult to identify the boundary of some device terms, especially when they contain numbers and punctuations. And also, the sample size is relatively small on the device entities. And for the attribute extraction, frequency, route, dosage, strength, and form have high F measures, all with a value above 0.8. The duration attribute have a low F measure, possibly because of its various description. And for the attribute association, around 93% of the attributes are correctly associated with the corresponding treatment entities. And lastly, for the component relation extraction, only combined with relation contains incorrectly extracted and missed cases. And for the incorrectly extracted cases, it is either because that one entity is an explanation of the other one, or the treatment entities within an intervention snippet belong to different arms instead of a complex intervention. To conclude, we developed and validated an intervention representation along with an automatic normalization pipeline for complex interventions in PubMed abstracts. And our system has several advantages. First, compared with other systems, our intervention types are expanded from drug to include drug, procedure, activity, and device. And second, we introduced component relations that contains temporal, spatial, and Boolean type relations between the intervention components. And we also proposed a hybrid approach integrating dependency parsing and pattern matching for attribute association that covers most of the association cases. This work is supported by the NLM grant, bridging the semantic gap between research eligibility criteria and clinical data. All the source code is available online. If you have any questions, please feel free to contact me. Thank you.